Good afternoon to scientists around the country and around the world. My name is Ziad Ghanem, and I'm an assistant professor here in the Department of Chemistry at Yale University. Give me just a second. And I'm very proud to be kicking off what has been a tremendous effort to distill, separate, and recrystallize all of the thoughts, concerns, and questions we had about applying to our graduate program into 2.5 hours and deliver something that may be generally helpful for chemistry graduate school or STEM graduate school perspectives. Now, don't get me wrong, this program is 3.5 hours, but we've got an hour set aside to answer your questions. The moderators will be communicating those to us from you in the Q&A. This chemistry bootcamp is a product of our department's Diversity and Climate Committee, which draws on the strength of all members of our community. Students, postdocs, staff, alumni, and faculty. Chemistry has been responsible for some of the most significant improvements in our quality of life over the last century. The discovery of antibiotics and other pharmaceuticals, the advent of computers, and the development of industrial methods such as the Haber-Bosch process to produce fertilizer all have required fundamental advances in chemistry and have had profound impacts on society. In the next century, it is likely that chemistry will play a central role in the development of alternative energy vectors to replace fossil fuels, the realization of practical quantum computers, the discovery of new methods to treat and prevent diseases, and the adoption of more sustainable industrial processes. That's a guiding statement from our handbook. A chemistry PhD at Yale provides students with the technical foundation to both appreciate the scientific basis for previous discoveries and to develop the fundamental skills required to make future breakthroughs. Under the tutelage of world-leading researchers, our department's research encompasses these sub-disciplines of chemistry: organic, inorganic, physical, biophysical, theoretical, materials, and chemical biology, with many of us, maybe most of us, crossing over. Now, research, what does this mean? In chemistry, research is like quantitative puzzle solving. My friend suggested that it was like doing Sudoku or playing chess. In my lab, we develop and apply microscopies that let us study chemical reactions one molecule at a time. And I personally think playing with the rules of nature is the most beautiful game anyone can play. But regardless of what it is you like about molecules, we all agree we find chemistry fun. But you don't have to take my word for it. Today, you'll hear from 6 panelists about their pathways through research, in research, around research. And although research is a huge component of graduate school, it's not everything. In addition to those technical skills, you will learn a wide variety of transferable skills, such as critical thinking, oral and written communication. If you've written anything, you know that writing is a creative process. And yes, there is a ton of room for creativity in chemistry. You will get to watch yourself transform from a consumer of knowledge to a teacher and producer of knowledge. You will find yourself constantly a student and a teacher. Mentoring is an important professional skill in both academia and the real world. Being a mentor, working in a team, and thinking about how to prioritize risk versus reward, these are all professional skills that people can benefit from during a PhD in chemistry. In addition to these professional benefits, there are compensation benefits. If you are accepted, then you will attend for free. And by that, I mean your tuition is paid for you, in most cases by your research advisor, and you will be paid a stipend. This includes health insurance and a variety of Yale student perks. So rather than tell you about research, I'm going to show it to you. When considering a higher education in chemistry, one can take a short-term view that they enjoy doing chemistry as an undergraduate and want to continue doing it, then see what doors that leads to. In the long-term view, a chemistry PhD is what you are using to get to a particular career point. So as such, we are presenting both sides of research. You will be hearing from my colleagues, introducing what they do and showing you results from their research groups. Then we'll have a 5-minute break, if time allows, and we'll meet 3 outstanding Yale alums before they answer your questions. And without further ado, I would like to hand it over to my friend and colleague, Professor Sharon Holmes Schiffer, John Gamble Kirkwood Professor of Chemistry. Take it away, Sharon.
Okay, thank you, Ziad. I'm going to talk about the emergence of theoretical chemistry as an area that has really been flourishing, and it's an area that I work in myself. So just to give a brief history, before the 1980s, theoretical chemists mainly worked with a pencil and a paper. They derived equations, they looked at toy models. Usually each department had maybe one theorist who was kind of stuck in some back room and really didn't interact that much and wasn't really all that considered all that useful. But fortunately, things changed. So from the 1980s onward, computers got faster. There were new algorithms, and now theorists started to be able to look at real systems. And now departments have multiple, several theorists per department, and now they're actually well integrated and they're working very closely with the experimentalists. So when we start thinking about how to apply theory to chemistry, it turns out that we need to worry about quantum mechanics, because molecules are composed of atoms that are connected by chemical bonds, and these chemical bonds involve shared electrons. And shared electrons require a quantum mechanical description. And chemistry also involves the breaking and forming of chemical bonds. And in order to describe chemical reactions, we need to use quantum mechanics. So to do this, we solve the Schrödinger equation for the electrons, just H side equals E side. And so then we can do quantum chemistry on molecules such as this benzene right here. And then you can look at geometries and relative energies. You can look at molecular spectroscopy on the computer. And so calculations now are helping to interpret experimental data. As I said, there's a lot of collaborations now between theorists and experimentalists as we help them. Now, in recognition of the importance of quantum mechanics, the Nobel Prize in Chemistry in 1998 was given to two people who made quantum chemistry practical for larger molecules. So this is Walter Kohn for his development in density functional theory, and John Pople for his development of computational methods and more wave function-based theories. So these two people and their contributions, as well as many, many others, have made it so that we can now do quantum chemistry on fairly large molecules, and we can look at spectroscopic properties and and look at chemical reactions involving small molecules. But what if you want to go beyond molecules and you want to look at something like a protein? So here's a picture of a protein. A crystal structure will tell us what the structure looks like, but what if we want to see how it moves and look at the chemical reactions? Well, it turns out that quantum mechanics on these really, really large systems is still not possible. We need faster methods to be able to look at these kinds of larger systems. So for this, people have developed molecular mechanical force fields, where each atom is represented as a ball, and then each configuration of atoms has a potential energy associated with it. So for something like a protein, we can describe the atoms in a bond, a chemical bond, just as two spheres connected by a spring. And then we can describe what are called non-bonding interactions, two atoms that aren't connected by a chemical bond, by steric interactions, so they're going to repel each other if they get too close, and electrostatic interactions where opposite charges attract and like charges repel. So you can put all of these interactions together and describe what the potential energy is of a protein. In this case, we don't have to do quantum mechanics. We don't have to solve H side equals E side. And if we want to understand how proteins move, then we can do molecular dynamics. So what molecular dynamics is we just solve Newton's equations of motion. So force equals mass times acceleration. So probably all of you back in, probably just high school physics or something, learned how to tell what the position and velocity of a baseball is. If I tell you the initial position at time t equals 0, you can tell me where the baseball is going to be and how fast it's going to be going at a time t later. So what we do with molecular dynamics is we do the same thing that you would do with a baseball, but for a baseball, the force on it is just gravity. But now for a protein, we just have lots of these spheres. Each sphere is a different atom. So instead of just one baseball, we have all of these, and the potential energy is much more complicated than just gravity. But we can get the forces from the potential energy, and then we can learn what the locations of all atoms at all times are. And this can all be done on a computer. So for example, this is a protein DNA polymerase eta. This is a protein that we've been studying in my group. And it's very important because it plays an important role in preventing skin cancer. So when UV light shines on you, it can cause mutations. And these mutations can cause problems in DNA replication. And this protein here can bypass those problems. And you can see this thing is wiggling here. What we're doing is we're solving Newton's equations of motion for this protein and seeing how it moves. And that helps us understand how it works and helps us understand how we can modify it to do different types of chemistries and to do it in different rates. So that's all fine and good, but we're just looking at this thing wiggle. We're not actually looking at do chemistry. And the whole point of enzymes is that they catalyze chemical reactions. So we really want to look at chemical reactions in enzymes. But for this, we need to look at bonds forming and breaking in large systems such as protein, or maybe just in solution in a big box of water. But in order to do this, we need to use quantum chemistry methods, because quantum chemistry, as I mentioned, that's required to describe breaking and forming of bonds because of the electrons being involved in chemical bonds. And those are expensive for big systems like proteins. But we know we have these molecular mechanics methods that are cheap, they're very fast, but unfortunately they cannot break and form bonds. So what do we do if we want to look at chemistry in a big system like an enzyme? Well, what we can do is we can combine quantum mechanics and molecular mechanics in what's called QMMM methods and treat the active part where the chemistry is going on quantum mechanically and the rest of it with molecular mechanics. And then we get the best of both worlds. And this led to another Nobel Prize in 2013 for 3 people who have developed multiscale models for complex chemical systems. So these are just some examples of the types of theoretical chemistry you can do: quantum mechanics, molecular mechanics, or mixed, QMMM. And just to give you an idea of the types of systems that we look at in my group, we've looked at applications of theory to catalyst design. So in this case here, we design catalysts, these sort of rose-colored C's here, to take electrons from an electrode and protons from solution and make H2 to make molecular hydrogen. And the objective here is to design these catalysts with a high turnover frequency. So we want them to be very fast and a low overpotential. We don't want to have to put too much energy in. And we want them to be environmentally friendly and cost effective and earth abundant. So here are some examples of a cobalt catalyst and a nickel catalyst that we've been developing in my group to generate hydrogen. Another example is artificial photosynthesis. So photosystem 2, which plays a role in artificial photosynthesis, splits water into hydrogen and oxygen. And it does this by taking this tyrosine residue and oxidizing it, taking away an electron, which it then makes the tyrosine give a proton to a nearby histidine, which has been postulated to give its proton to something else, creating a proton wire that you can pump protons over long distances. Now, it's not clear that this particular proton wire necessarily occurs, but we know in many biological systems these kinds of proton wires do exist. And so the question is, can we follow nature's example and assemble a proton wire, where now we use an electrode to take out the electron? And we can get 1 proton or 2 protons, and in fact, we've designed these kinds of wires to get up to 4 protons to transfer just by removing an electron. Another example is a biological example. This is a BLUF photoreceptor protein. BLUF stands for blue light using flavin. So when you shine blue light on this protein, it basically leads to a proton-coupled electron transfer reaction, which is called PCET, where you have both electron and proton transfer simultaneously. That leads to conformational changes in the protein, which then can turn on or off an effector that's 50 angstroms away. So this BLUF, coupled to this kind of an effector, can cause changes under blue light. It can cause neurons to fire, reactions to be catalyzed. So for example, this rat here, it's got this probe embedded into its brain, and by shining blue light on it, you can get the rat to do different things. And this is relevant to optogenetics, where light is used to manipulate cells and living tissue with very high spatial and temporal resolution. So the idea is to use these kinds of methods I've been talking about to study this process. And for this, we need to use QMMM, the mixed quantum and classical methods, where we treat this part of the system that I'm circling here. That's got to be quantum mechanical, because you've got bonds breaking and forming. But the rest of it, we're just going to treat with regular molecular mechanics. And we can do a simulation where we first photoexcite it, we shine light on it, and then we photoexcite that flavin, and you can see what happens then in this movie right here. So we photoexcited, we have electron transfer. Now you see these protons, these 2 white protons transferred, and you saw a rotation of this glutamine here. That kind of a rotation we can see on the computer, but they cannot see it experimentally. And then you're going to see a back proton transfer. These guys are going to go back again. There they go. So basically, this kind of a QMMM molecular dynamics simulation can tell us the whole photocycle, and then we can characterize this light-adapted state at the end that can transmit a signal to do something like optogenetics. And we can see things on the computer that cannot be seen experimentally. So these are examples of some applications, and you might think, well, these guys, there are 2 Nobel Prizes given to theoretical chemists. That must mean that, they know how to do everything. Everything's been developed. But it turns out we still need to develop new methods too. And so in my group, we've been developing what's called a nuclear electronic orbital, or NEO method, where instead of solving the electronic Schrodinger equation, H psi equals E psi, where all the electrons are responding instantaneously to the nuclei, that's the Born-Oppenheimer approximation. We are saying, let's take certain nuclei, protons, they're the lightest ones, right? Hydrogen's the lightest element, and let's treat them quantum mechanically too. And so we now solve a nuclear electronic Schrodinger equation. And this way we can include nuclear quantum effects like zero-point energy and hydrogen tunneling, and go beyond the Born-Oppenheimer approximation in a computationally practical way. And we can calculate pKa's, geometries, reaction paths, tunneling, splittings, isotope effects, and all sorts of different properties with this new method that we're developing. Most interestingly, we can actually do dynamics. So we can integrate, remember before I was talking about Newton's equations of motion, classical equations of motion. Well, we can also integrate the quantum mechanical equations of motion, the time-dependent Schrodinger equation for the nuclei and the electrons all together. And that's what's happening here. We photoexcited this molecule here to an excited electronic state, and we can look at what the electrons and the protons are all doing as a function of time, and look at their non-equilibrium dynamics for, say, proton transfer or for proton-coupled electron transfer. So these are just a few of many examples of what you can do with theoretical chemistry. And what we're doing in my group here at Yale, and there are other groups at Yale also doing theory, and then you're going to hear from some experimentalists as to what they can do also in their labs. So just listing the projects here, and I'd be happy to talk to anybody or answer questions during the Q&A. You can email me if you have questions that you want to ask that way, or look at my group website. Thank you very much.
All right, thank you so much. Next, we're going to be hearing from my friend and colleague, Professor Jason Crawford, who is the Maxine F. Singer 57 PhD Associate Professor of Chemistry and Associate Professor of Microbial Pathogenesis. Take it away, Jason.
Okay. Okay. Yeah, thank you for the introduction. Like Ziad said, my name is Jason Crawford, and I'm going to tell you about chemical biology at Yale University. So my lab, like Ziad said, again, I'm a professor in chemistry, but we are also working in microbial pathogenesis, chemical biology. And my lab shown here, we are on Yale University's West Campus, which is one of 3 state-of-the-art campuses at Yale. So let's start with, well, what is chemical biology? And Kornberg said it nicely 25 years ago. Really, if you take medical disciplines, things like anatomy, physiology, and etc., really all of them, they can be expressed in the universal language of chemistry. Therefore, biology can be understood in chemical terms. So really the goal of chemical biology research is to use the universal language of chemistry to understand biological systems. And that includes their perturbation, like drug development. So what is biology? I borrowed this slide from the internet, and like most things on the internet these days, it's filled with some inaccuracies, and unfortunately that's true in science as well. The reason I use this in first year classes, I say, well, what is missing? And the students that are really dialed in say, well, you're missing reverse transcriptase to go from RNA to DNA. We then have a 10-minute discussion on things like DNA methylation and other epigenetic modifications, RNA splicing and modifications, as well as post-translational modifications of proteins. After about 10 minutes, I ultimately just give them the answer. And it's really small molecules. I mean, small molecules are the central missing link of the central dogma. And if we go back to an abiotic world before life existed, you had geochemical cycles, and those cycles, some of them ultimately got programmed into biology itself. Now, as nicely stated by Schreiber about 15 years ago, chemical biology, in terms of his blue arrow there, points to the small molecules. Small molecules can interact with other small molecules. They can interact with DNA, like intercalate or alkylate, changing the programming. They can interact with RNA, like riboswitches, to alter expression programs. And then they can bind to proteins as drugs, or they can be made by proteins. So they really, you can see that they're the central part and they interact at all levels. Now, chemical biology stems, at least modern day chemical biology stems from organic chemistry. But we take a kind of broader view nowadays. And as long as you break biology down to molecular bonding and chemical reactivity, we call you a chemical biologist. So we're a very inclusive discipline. So because it's so very, very broad, you can apply chemical biology in many different ways. So I'm just going to use an example, focusing on the human microbiome as one of the modern areas of chemical biology. We know that the microbiome is critical to human health, clinical responses to drugs, as well as disease initiation. You'll be happy to know that there are many groups in chemistry that work on the microbiome. And in fact, there are groups in about 6 different departments here at Yale. And we have a very strong network to study this area of science. So what do we need to think about? We need to think about genetic context, right? Disease polymorphisms in the host, like you or me. And we need to think about the environment. We acquire all of our microbes from the environment. And of course, our diet is going to dramatically affect these processes. But all of these processes can be really dialed down into chemical consequences. So 2 things I really want to point out, and this is incredibly important. The vast majority of metabolites, so small molecules of metabolism that are found in any cell, no matter what organism, remain unknown. Human cells, 90% of the molecules, we don't know what they are. So one key area of chemical biology is figuring out which ones of those molecules are relevant biologically, figuring out what are their structures and what do they do. And I would argue that the next blockbuster drugs or signaling molecules are already there, and we just need to fish them out and identify them. The other area that's incredibly important is the bottom right. These metabolites can be diffusible functional entities. So even if a microbe in your gut makes a molecule and reaches systemic circulation, it might function in your brain. So in that sense, they're diffusible functional entities, and that allows us to have what we call a small molecule centric viewpoint of biology, i.e. chemical biology. So if we come to the chemistry at the host-microbe interface, this is kind of a simplified schematic that we think about. In A here, you can see that this kind of type of line is for inhibitory functions. So they produce things like antibiotics that you can isolate. C, these are cooperative behaviors among microbes, like chemical signaling. F are exchange factors that promote growth. But then if you look at the interface itself, microbes can inhibit or activate host responses. And then the host can in turn inhibit or activate processes in the microbiome. And it's dysregulation of these individual processes that can lead to disease, many diseases. In fact, many of these diseases we can boil down to cellular stress signaling programs. So 2 molecules on the right that we and others have worked on. The left molecules we call the colibactin warhead. That's associated with colorectal cancer initiation. And the molecule on the right is called tilivaline, along with this other molecule called tilimycin. Those cause hemorrhagic colitis. So these are just kind of 2 examples where small molecules in your gut cause disease phenotypes. Okay, so coming back to cellular stress, if disease can be thought of in terms of cellular stress signaling programs, I have a little section here I call Stressed Out, the chemistry of cell-to-cell stress communication. And I've just borrowed some examples from my group, but this is universal. You know, all sorts of examples are there. So one example we call quorum sensing in bacteria, where as the bacteria increase in numbers, so too do the molecules that they produce. These lead to programs like pathogenesis. And this very simple molecule, you say, oh, it's extremely simple, but that simple molecule regulates pathogenesis at 5 nanomolar concentrations. But if you apply a cellular stress to those pathogens, you can see that subsets of those molecules have differential responses. So a lot of these chemical signaling programs consider chemical sensory inputs in terms of directing these chemical outputs that we need to think about. So that brings me to another example I like to call cell extrinsic chemical signaling. And in this regard, you might have a pathogen that may respond to a host immune response up top or some sort of antibiotic treatment. And in this regard, these bacteria or pathogens can respond. And those little green circles are small molecules. And this can lead to what we call preemptive adaptations. That is, the other microbe not yet experiencing the stress can recognize a chemical signal and launch an appropriate response. And this is important for antibiotic resistance. So one example where we've shown this is, again, simple types of molecules that regulate these really critical chemical signaling processes. Other examples include antibiotic synthesis. We can take microbes, stress them out in the lab, and get them to turn on their own warfare programs. And then we can discover those molecules, many of which are antibiotics. One example from the group is this really complex hexacyclic carbocycle, as shown here. And if you apply a cellular stress, you can see activation of this defensive response. But this is just one example, and we and others use these sorts of examples to discover all sorts of wonderful, structurally interesting molecules, from nucleotide analogs and heterocycles in the bottom right, glycoamino acids on the bottom left, or opine glycopeptides on the top left. And those regulate signal transduction in human cells, such as G protein-coupled receptor signaling. So lots of wonderful chemistry, but this is not limited to microbes. They affect human signaling programs. They produce immunomodulators, virulence factors, and serve as a wonderful reservoir to discover new pharmacologically relevant molecules. And one example that I pointed to at the beginning is the production of these molecules that turn on DNA damage responses. So P53 is just a DNA damage response. One aspect of cellular stress chemical signaling. And that molecule, again, coming back to here, just zooming in on the warhead motif itself, is the Colibactin warhead, right? So colorectal cancer initiation all comes back to much of which are stress signaling programs in cells. Now, the other thing I want to point out, this is kind of the last feature I want to point out, is I said that most molecular features or small molecules found in any organism remain unknown. And that also includes human cells. 90% of human cells, we don't know what those are. So one aspect of my group, we're actually decoding novel small molecules in the immune system. And in cases of inflammatory diseases, sometimes you just have dysregulation of those small molecules. And then you can take those small molecules right out of the box, right? No med chem required because they're the natural ones. And you can put them back in and restore homeostasis. So this is a wonderfully exciting area called immunometabolism. And it's all chemistry. So that brings me to my last slide, and I've jokingly quoted myself now. Small molecule therapeutics for the treatments of some of our most debilitating diseases are already functioning at the human microbe interface, and they simply await discovery. And that's where you guys come in. You know, these are thesis projects, not just in my group, but in lots of chemistry groups at Yale, discovering the underlying molecular mechanisms of disease modulation. That is chemistry. And that's all I have, and I'm happy to take questions in the Q&A. Back to you, Ziad.
Thank you so much. Next up, we'll hear from my friend and colleague, Professor Jim Mayer, who is the Charlotte Fitch Roberts Professor of Chemistry. Take it away, Jim.
All right, thank you, Ziad. It's a hard act to follow my two wonderful colleagues, and I thought I would start more generally. I'm an inorganic chemist, as I'll show you in a second, and I think a lot about what graduate school in chemistry is like for the students who work with me. And I want to emphasize to all of you watching that it's really a special time. It's not all a bowl of cherries. There are ups and downs in it, but it's a special time. Did I start my video? I'm sorry. Okay, so here are my slides. And you can see me now. I find graduate school is a really exciting time to focus on your science, to learn a lot of new science and to discover a lot of new science. As Ziad said at the beginning, you get paid, so you don't have to worry about how to survive. You don't get rich as a graduate student, that's certainly true, but your tuition is paid for and you get a stipend. You generally pick an advisor working in an area that you're very excited about, and then you and your advisor get to decide what you are going to work on. And then you work intensely on a set of projects for a number of years. You become a world's expert on your narrow topics. And work in a research group is you work together with other students, but it's very individualized. Every student has a different experience. I think it's very different than other school situations where everybody is sitting in the same classroom. Some graduate students focus on one project, some do a whole bunch of projects, some set up collaborations, some work in multiple areas. I just thought I'd show you a picture of my group after a group outing last summer before all this craziness hit us. I just want to emphasize in this sort of philosophical part of my remarks that being a graduate student is almost more like being an apprentice than being a student. An apprentice learns from the mentor, but also learns tremendously from the other apprentices. And I think that's the way research groups work, is the graduate students support each other. They learn from the professor, but they also learn from each other. And then when they're done, they're certified like an apprentice to go off and be able to teach or do many, many other things. And you'll hear from some of our alumni about all the different things that they're doing outside of universities. So what do inorganic chemists do? I'm afraid in 10 minutes I can't tell you that because we work across the whole periodic table. And I mean, I'm inspired by Jason's work and his brief description of it. But from an inorganic chemist perspective, they're stuck up here in the top right corner of the periodic table, just a few elements. And in my view, many of the really difficult chemical things that nature does, that biology does, involve the rest of the periodic table. Many of these metallic elements are involved in what we call bioinorganic chemistry. For instance, iron and hemoglobin to carry oxygen around the body. So inorganic chemists look at those kinds of problems. And I would say inorganic chemists are part of what chemists call the central science. Lots of inorganic chemistry effects is related to what happens in geology, in the mineral water interface, for instance, in the environment, in toxicology. All of these different areas are related to different parts of chemistry, and I would say inorganic chemists touch all of them. I just thought I'd mention one project right now because it's just been funded. This is actually a major hub that was just funded by the US Department of Energy. It's based at the University of North Carolina, but there are 5 Yale faculty involved. That's the dark blue color of Yale here, shown around my picture. Actually, the funding has not actually arrived. It comes next week. But this is going to be a team of about 30 faculty who work together on all different aspects to try to take CO2 and water to liquid fuels. Here I've just shown in the bottom right here methanol as one potential liquid fuel. As Sharon pointed out, the energy problem is a huge problem in this century. We need to find non-polluting, inexpensive forms of energy, and the sun is a great way to do it. The problem with the sun is when it's not shining, you don't get any energy from the sun. So you have to have a way to store the energy. And for millennia, humans have used chemical fuels as ways to store energy. So the question is, how do we turn sunlight into liquid fuels that can then be put in a gas tank, can be put in a tank under your house to heat your house in the winter, right? So CHASE, this is the Center for Hybrid Approaches in Solar Energy to Liquid Fuels, has a 5-year research goal, and we have $40 million to do this, to develop at a molecular level, at a chemical level, an understanding of how photoelectrodes and molecular catalysts can be all integrated together to accomplish reactions of this kind. So this is a very diverse team. There's a team that works on, there's a group set of people that work on semiconductors of all different kinds that might absorb the light and create electron hole pairs and separate them. What you need to take CO2 and water to methanol in particular is the electrons. And we envision that those electrons will be connected through some linker to a molecular catalyst that will not only interact with CO2, but will turn it into specifically what we want. And that's one of the great challenges, is not to make 47 different molecules, but to try to make one molecule that, that has real value so that the whole thing can be economically feasible. So this is one of the many challenges facing inorganic chemists. And I thought I'd just describe it briefly. We have 5 years to do this team, and I'm excited to work collaboratively with my colleagues and colleagues around the country on this. So this is one of the mountains that we have to climb. And I think with that, I'll just turn it back to Ziad, and hopefully we're still on time. And like the other speakers, I'm happy to answer questions in the Q&A or in the panel discussion to come.
All right, thank you so much. It would be nice to see more of people's questions in the Q&A, so please keep those questions coming. I want to thank all 3 of the faculty panelists. Next, we're going to be taking a 5-minute break before we hear from our Yale alum panelists. So thank you all very much for joining us. Welcome back. Now we'll hear from three outstanding Yale alums who have gone on towards policy, towards pharma, towards entrepreneurship. They will share their paths through science and answer your questions. Our first panelist is Dr. Julie Carruthers from the United States Department of Energy. Take it away, Julie.
Thanks, Ziad. Good afternoon, or good morning, or good evening, depending on what time zone you're in. It's really great to be with you here today. So I graduated with my PhD from the Yale Chemistry Department in 2001. And for the last 10 years, I've been a senior science and technology advisor and program manager at the U.S. Department of Energy's Office of Science in Washington, D.C. So for those of you who aren't familiar with the DOE Office of Science, it is the largest federal sponsor of basic research in the physical sciences. So that's areas of physics, chemistry, high performance computing, computer science, and targeted areas of biology and environmental research. Our budget is about $7 billion annually, and we fund competitive research at hundreds of universities across the country and at 17 Department of Energy national laboratories. And as you heard from Professor Mayer, he just recently spoke about one of our awards in the area of solar fuels, and just a quick plug, that sounds like a really fantastic opportunity for grad students. We also build and operate large-scale scientific user facilities for the research community. These are everything from the fastest computers in the world for open science, X-ray light sources, and neutron scattering facilities for molecule and materials characterization, large nanoscale science research center for the synthesis and characterization of nanomaterials, high-energy particle colliders for high-energy physics and nuclear physics, and long-term atmospheric measurement field sites for Earth system science research. All of these are open to the researchers across the world on a competitive basis, and they serve and support the research of over 35,000 people annually. So as a senior advisor, I'm responsible for areas of strategic planning and new initiatives. I'm also responsible for science policy. That's both policy development as well as developing action plans around responding to and implementing new policies that are established by Congress and the White House. I've been responsible for creating and implementing new research programs within the Office of Science, as well as new STEM training programs. And I lead initiatives to advance what I call organizational excellence. And so one recent example of that is a focused effort to advance diversity, equity, and inclusion, and how we execute and manage our research awards at universities and the DOE national laboratories. So that's a little bit about where I am now, and so how I got started. Really, actually, it goes back to having a fantastic high school physics teacher, and that really is what got me to pursue science as an undergrad. As an undergrad, I had the opportunity to take a work study position as a sophomore doing research on rhodopsin in the lab of David Klieger at UC Santa Cruz. And that research experience really inspired me to pursue a PhD in chemistry. I loved really doing experimental research. And from my junior year as an undergrad, I really had my sights on getting a PhD. Well, for the end of my PhD, I was looking at a number of career options. Including academia, but I really wanted to work in an area that was different from the one that I did my PhD in. And I ended up landing a fantastic opportunity to take a Dreyfus Foundation postdoctoral fellowship in environmental chemistry at the University of Massachusetts. The fellowship is really specifically for chemistry PhDs who wanted to retool in environmental chemistry. As a grad student, I had been working with the local Trout Unlimited chapter in Connecticut on river water quality issues. And that was really my first exposure to providing scientific advice to elected officials. And pursuing environmental related research questions started to really appeal to me. And so this particular postdoc opportunity seemed like a great fit. One of the things that attracted me to this particular department at the University of Massachusetts was that the faculty were made up of physical scientists, so environmental chemists and physical oceanographers, as well as experts in natural resource management and environmental law. So it was truly an integrated department of disciplines in their research, as well as the degree programs that they offered. And while I was a postdoc, I ended up serving on an advisory board for a group that was advising the city of Boston on water quality issues in Boston Harbor. And again, that showed me how important it was for decision makers to incorporate sound science in their decision making. And so at the time, I was thinking more seriously about pursuing a career in science policy. I ended up applying and received the American Chemical Society's Congressional Fellowship and ended up working in Washington, D.C. in the office of Senator Dianne Feinstein, who is one of the senators from California. And this was really a transformative experience. I loved the opportunity to use my science expertise in research and research new topics for her and use that knowledge to provide advice in making decisions both on policy and legislative actions. So during that time, I was still continuing my postdoctoral research. Back in Boston, I was going back and forth. It was a little crazy, but I hadn't really decided what direction to go in. I had applied to faculty positions, and when I had an offer in hand, I really realized that I liked the kind of work that I was doing in DC. So I took another fellowship with the American Association for the Advancement of Sciences, Science and Technology Policy Fellowship Program, and ended up in the Department of Energy's Office of Science for 2 years as a fellow, and then found a great opportunity to stay as a federal employee. So this experience really opened my eyes, you know, being in Washington, opened my eyes to career opportunities in federal agencies. It wasn't something that I had been exposed to at all as a grad student. And career opportunities, not just the Department of Energy, but the National Science Foundation, NOAA, NASA, EPA, Department of Defense, all of them employ hundreds to thousands of PhD scientists. Some of them are doing research, some of them are managing research grant portfolios, grants to universities and other organizations. And so the deep skills one develops in a PhD program are absolutely translatable to these careers. The ability to teach yourself any topic, project planning, data analysis, the ability to communicate technical information to non-experts. These are really translatable skills, and they're a great opportunity for PhD scientists in the federal government. While I don't do chemistry anymore, I think once a chemist, always a chemist. And so I regularly use my chemistry skills in cooking and gardening, and it continues to be an outlet for experimentation. So that's my career pathway in a nutshell, and I'll hand it back to you, Ziad.
Oh, thank you very much. Thank you very much. Next up, we will be hearing from Dr. Kate Otley, who is Senior Product Manager at Takeda Pharmaceuticals. Take it away, Kate.
Everyone, thanks, Ed. I appreciate it. I actually don't often get called a doctor, so that's very fun. Well, it's great to meet you all, and excited to share a little bit about my journey to get my PhD at Yale, and then a career journey afterwards. A little bit of background first. I completed my undergraduate degree in chemistry at Hamilton College, which is a small undergraduate institution in upstate New York. And while I was there, I had the opportunity to conduct some summer research at Hamilton, and then also at the University of Massachusetts Amherst through an REU program. It was a really great opportunity. So if anyone's looking for summer research, I would highly recommend looking into an REU. It stands for Research Experience for Undergrads. At Yale, I completed my graduate studies with Dr. John Ellman. I graduated about 3 years ago in 2017. And I joined the Ellman Lab really with the goal of doing work at the interface between chemistry and chemical biology. So in the group, I actually got to work on a number of different projects, ranging from true reaction methodology development using rhodium catalysts to create heterocycles, all the way to building and designing small molecule enzyme inhibitors informed by crystal structures. So really got a wide range of projects and had the opportunity to learn a lot of different things. I really enjoyed it. My path to science. So I always liked science, but I actually fell in love with organic chemistry, specifically in college when studying aldol reactions. I remember just doing the reaction mechanisms and thinking they were so graceful and flowing, and that's really what did it for me. Greatly enjoyed my PhD work, learned so much, made so many good friends at Yale. And following graduation, I really wanted to pursue an impactful career in the life science space and take what I had learned and make a real impact. So I first, directly after graduation, spent 2 years as a management consultant at the Boston Consulting Group. And there I really got to learn about business and how I could leverage my scientific background to make a real impact. Some of the projects that I worked on include disease area strategy, so identifying unmet needs in neuroscience that would make sense for a company to invest in, I worked on projects around launch strategy for medical technology companies. And then I also worked on a few projects around marketing strategies. So, you know, there's a drug, which HCPs should be really interesting, and I learned a lot. And now I'm working in the neuroscience business unit at Takeda Pharmaceuticals, which is a global biopharma company. I love my job. It's really exciting. I get to work with an awesome team of people. And what I do is really centered around education on our disease state and area and some of our products. So we take clinical data and the FDA approved label for different products and figure out how we're going to educate healthcare professionals around that data. What is our strategy? What medical congresses should we be bringing this to? How do we develop insights about the market through discussions with key opinion leaders, competitive analysis of other things out there in the market? So it's really interesting, and I love it. And I would say one of the great things about my graduate career at Yale was that I really had the opportunity to try a lot of different things. There's so many opportunities. So I really got, of course, lots of exposure to science and chemistry, but I also got to dip my toes into business a bit through the consulting club and a number of other opportunities. Okay, so getting my PhD in chemistry. I always have loved learning and wanted to continue learning as long as possible. I was sort of mind blown by the prospect that after undergraduate, I could go and continue school and get paid. I thought that was amazing. So I just wanted to continue learning as long as possible. And then towards the later half of my graduate career, I thought about lots of different career options. I thought about doing a postdoc, trying to get a position as a professor at an undergraduate institution, of course, management consulting. I also explored things like patent law, bioequity research. Doing your graduate work at Yale, you really just have so many opportunities. On campus, there's lots of different clubs you can get involved in. There's also lots of different companies that come and educate you about opportunities. There's constantly pharmaceutical companies coming to give talks and presentations. So I really felt like I got to learn a lot about many different career options after graduation. And then I think in my current role, I really leverage so many of the skills I learned during my PhD. I would say probably the biggest one for me is the ability and sort of confidence to take on ambiguous problems without a lot of direction and work through uncertainty. Science literacy, of course, is another thing that comes up all the time. So it's really important for me to be able to understand the mechanism of action of different drugs and interpret clinical data. And then also you get a lot of credibility by having that doctorate as well. And then I have a fun fact on this slide also. During graduate school at Yale in Connecticut, I actually got very invested in hiking in New Hampshire. So I have this new lifelong goal of hiking all 48 of the 4,000-foot mountains in New Hampshire. I just completed my 32nd, so it's something I've been doing since around my second year in graduate school. So, thanks, everyone.
All right. Next up, we will be hearing from Dr. Jacob Black, who is the CEO and co-founder of Treehouse Hemp, in addition to being an alum from my lab. Take it away, Jake.
Thanks, Ziad. And yeah, thanks for inviting me to this. It's exciting. So I'm probably the most recent graduate here. I finished up my dissertation in 2019 and have kind of gone on a different route into entrepreneurship and the startup life, which has been really exciting. But yeah, just jumping into my background, I did my undergraduate degree at Villanova University out in Pennsylvania, and was really fortunate in my kind of sophomore year to get involved in research and really enjoyed the lab that I joined, did 2 summers of research, and then did pretty much every semester, so almost 6 semesters of research. So I really kind of caught the research bug at that point and knew it was something I was interested in. That said, I was doing all my research in organic chemistry and medicinal chemistry. And so when I went to Yale, that's what I was planning on doing. But I met Ziad, and he was a new professor there, and I was really interested in the projects that he was pursuing. And so right off the bat, I went on a kind of path change right then, and did my dissertation in developing new methods of single molecule spectroscopy, which I really enjoyed. I got to do, I still got to do organic chemistry, polymer chemistry, materials chemistry, spectroscopy, and really work on a lot of different projects. And so that really fit what I wanted to get out of graduate school. And I think, as everyone else's talk today is, you know, you can kind of get what you want out of it and make your kind of unique experience what you want it to be. I also participated in a bunch of the different chemistry kind of clubs or activities while at Yale. And so the Joint Safety Team and the Social Hour Committee are both within the department, organizing events around safety awareness, as well as kind of getting people together outside of just your lab. And then I did a lot of outreach with Pathways to Science and Science Saturdays. And so those programs are more about reaching out to the community and educating you know, younger students, high schoolers, middle schoolers, elementary school students in science, and trying to get more people interested in science. And so that's kind of my background. My path to science was really kind of, again, odd. I went into undergraduate and I was undeclared for actually the first 2 years. I was looking at potentially philosophy, history, English, but maybe biology, genetics, or chemistry. And I enrolled in genetics and organic chemistry and actually kind of fell in love with those classes, which is maybe not the average thing, but if you're here on this call right now, then you're probably one of those unique individuals. And so the concepts in organic chemistry, in particular stereochemistry, it was something I just never considered. One of those things that, you know, makes sense after you learn about it a lot, but the first time you hear about like non-superimposable mirror images, it just kind of blew my mind, and I just really wanted to go down that rabbit hole. And so going into the PhD, as was already brought up, I mean, chemistry is fundamental to so many different things, biology, physics, engineering. And so I didn't know exactly what I wanted to do, but I knew I loved chemistry, and I knew that I would find a way to apply it because it is so foundational to a lot of the kind of different fields out there. And it's very industrial applicable. So, you know, whether it's government stuff, pharmaceuticals, consulting, environmental space, like, you know, you can find a way to apply chemistry. And so that's how I chose to go into the PhD. When I was looking at, you know, postgraduate options, you know, academia, being a professor, consulting, potentially pharmaceuticals, and entrepreneurship. And I chose entrepreneurship, and that's the path that I'm on so far. My kind of, how do you change directions, which I've done a lot over, you know, the last few years, it's kind of go with the flow, which may not work for everyone. I know a lot of scientists are very planned out people who like to have a clear path, and I'm that way as well, but I'm also always open to opportunities and kind of following what I think is interesting and what I think is exciting. And so I've always kind of gone with the flow, and I followed you know, whatever is exciting me at that point in time, and also taking risks. You know, joining Ziad Lab is a good example of that. I was not a physical chemist. I was not, I had not done much spectroscopy, but I was super interested in it. And so I decided, you know, let's go this way and see where it goes. And same thing with kind of starting a company. It was, I have no experience in this, but let's go for it. And so that's how I kind of got there. With that, in my role, I'm now the CEO of the company. And so I do a lot of things as far as, you know, managing projects, hiring employees, budgeting, HR, you know, a lot of different things. But I think the skills from the PhD experience are very translatable. You know, you can plan a project and you can execute that project. And that's, you know, day in, day out, what you'll be doing throughout the PhD is you have this really long-term project, 4 or 5 years, that's going to take a lot of effort, but being able to plan and execute on that is very important, not only in grad school, but in anything you do after that. As other people have mentioned, the ability to process complex information, data, interpret it, come to conclusions, and then present it to other individuals in a way that's digestible, that, you know, makes sense to a broader audience. That's very important and has been super useful. And then again, other people mentioned this, but the ability to learn new skills constantly, to self-educate yourself and kind of incorporate that into your continual growth as a person. And so I didn't know anything about business or economics. budgeting, all of that. And you know, if you get a PhD in chemistry, I promise you can teach yourself accounting and budgeting. And so that's kind of the great thing, is you can teach yourself anything and go anywhere you want. And so something fun about me, I have a molecule tattooed on my butt, actually. And so that's a bit silly. I'm a bit out there. And then recently, during the last year, I've taken up painting miniatures, which I find very relaxing, I guess, especially in times like these. And so with that, I'll pass it back to Ziad. Thanks for listening, everyone.
All right. So at this point, we're going to be moving on to the question answer session, in which I'd like to invite any panelists that are currently not showing their video to turn video on, so they can field questions. And I will start by asking one of the questions from the chat about passion in graduate school. So the question reads, most people advise going into graduate school if you have passion for a subject and research. This may be an odd question, but what would you define as passion? How did you personally know going into something as intense as grad school was the right move after undergrad?
I mean, I can hop in here if that's okay, Ziad.
Of course, please.
Yeah, passion, right? Yeah, it's a tough one to define. I guess I almost use the word fascination more than, you know, passion. But like I think even in my graduate school application essay, I remember talking about like hiking in the woods and then translating that into like how I thought about everything from almost a scientific perspective, maybe not chemistry, but, you know, you look at leaves and then thinking about photosynthesis and electrons and you know, light is coming in this whole complex system that is just going on. And that really, you know, got me going. I was fascinated by that. And, you know, you look at rocks and you think about the different elements and structure. And so that is kind of how I describe my passion for science, is like, I can see it in almost anything. And it's always interesting to me, whether it's spectroscopy or geology or, you know, drug chemistry. And so that's my 2 cents there.
I guess for me, sort of similar. It was like mind share. So I would find that when I was taking chemistry classes in college, even outside of class, I was constantly just spinning and thinking about things in my head. I remember after taking PChem exams, I'd have a hard time falling asleep because all night I'm just spinning like, oh, did I do that right? I could have done it this way and derived it much more efficiently. Yeah, so I think that's how I saw my passion.
Yeah, so I think, you know, what everyone is describing is just this gravitation towards learning and curiosity, and I had, you know, a very similar experience. I loved being in the laboratory. I was happiest in the laboratory. I couldn't imagine doing anything else. So when I took breaks in the science library, as an undergrad, I would wander through the stacks and I would find random sections and sit there and read for an hour on something that I'd never heard of before. And I was particularly attracted to the column or the aisle on sleep studies, because I think I was trying to figure out how I could get by with the sleep, as little sleep as possible. But yeah, it's, you know, it's sort of where your mind gravitates to when you spend your time thinking, and what, you know, honestly, what makes you happy.
Jim, you look like you're interested to say something. Please go ahead.
All right, I'll just say that for many of us, probably it was the research lab that got us convinced. We had an interest in science. We enjoyed reading about science and watching shows about science. But the hook for many of us, and I encourage those on the call to try to get some research experience as undergraduates and get in a lab. And if it feels like that's the place for you, or behind a computer screen or whatever kind of, but not just learning the science, but doing it yourself and asking questions yourself. If that seems like fun and it's attractive to you, then that passion will carry you through the ups and downs of graduate school and on to other things, whether you continue to do research or not as a career. I think that's an important component of knowing that graduate school is the right place for you.
Fantastic. Another question that I just saw. This one is for Kate. How did you know industry was right for you? Did you do any internships throughout your doctoral program?
Yeah, great question. So I would first say I didn't know industry would be right for me. I thought I would like it, and I think any choice you make, you have to be brave and be informed and go for it. I'd say sort of doing your due diligence and understanding what the position will look like is of course really important. So networking was really key for me. I networked with a lot of actually Yale chemistry alumni and also alumni of my undergraduate institution that had similar jobs to learn about what they were doing, if they liked it, things like that. So I found that very helpful. I didn't complete any internships in industry during my graduate career, but as I mentioned, a lot of sort of industry and companies will come to campus, and there's often like sort of an educational presentation about a piece of research that they're doing or some science, and then an opportunity to attend a lunch and ask questions. So I think that's another great networking opportunity that I took advantage of.
All right. The second part of that question is for Jake. And the question reads, Jake, how did you break into entrepreneurship? What made you decide to go through leadership and not through marketing your own product? Did you own your startup? Did you start your own startup?
Yeah, no, that's a good question as well. Yeah, I did. I was a co-founder, and so a bit of I guess serendipity is the word I use, but I mean, I mentioned just kind of keeping your eyes out for opportunities and, you know, seeing what you're passionate about or what risks you want to take. But I had some people I knew, again, kind of this idea of networking, not really in the sense I think a lot of people think of networking as like this kind of selfish, like manipulative thing to like meet people who you can use to get to somewhere, but more about just being open to conversations and talking to people and asking questions. Like that's really all it is, just so to clarify that. But I knew people out in Colorado who were interested in starting this company in industrial hemp as it was becoming legalized. And really they were interested in one cannabinoid in particular, CBD. And as a scientist, I was interested in not only that, but all of these other cannabinoids that have never been studied. And so they had some business connections, and I knew them, and they knew that I was interested from a science perspective. And so we kind of just came together, again, develop a plan, executed that plan, and then have kind of just run with it from there. And so it was day one there. We started with 3 people roughly in a garage. Now we are at like 25 people. We went from manufacturing, say, a gram of product, you know, on a benchtop to doing roughly 200 kilograms a month. We built the whole facility from the ground up. And so I had no experience in any of that, except for some work I had done with Ziad starting his lab. But, you know, like I said, you can use the skills from the PhD. You know how to research things, you know how to execute plans. And so with those 2 things, you can, you know, pretty much do anything you want. And so that's really how I got into it.
Thank you so much. We've got some questions about the interdisciplinary nature of research. So one question reads, I'm interested in pursuing a career in bioinorganic chemistry, but I find the career path quite unclear. Can I get into it with a very biology intensive background? What's the knowledge required to enter the field?
I guess I should answer this one. Let me try to answer more generally, because I think a couple of the questions in the Q&A, I think graduate school is still school, and all of us who run groups feel that we can help students learn the material that they need to learn. There's much less requirement for background than you might think. I've had students join my lab who had very little background in what we do, and I've had my lab start things that nobody in the lab had any background in. If I didn't think I could help people learn things, I'm in the wrong profession. So I would encourage you to worry less about your background and more about the passion issues, because you can always fill in your background. This is what one of the things that we learn as a PhD is, as Jake said so nicely, is you learn how to learn. And so if there are gaps in your knowledge, and we all have gaps in our knowledge, you figure them out, you go find somebody to help you, you find books, you go to seminars, you learn those materials. And I think There are certainly bioinorganic chemists who started from a very strongly biological situation and learned the inorganic chemistry. And there are certainly inorganic chemists who got more and more and more interested in biochemistry and biology and moved more in that direction. And there's many examples of both. And I think that's important to the vibrancy of the field of bioinorganic chemistry. The Gordon Conference in Bioinorganic Chemistry was started by people who did EPR spectroscopy of organisms and saw these weird signals and didn't know what they were from. And what were called the pig feeders, those who knew that pigs needed a little bit of zinc and a little bit of cobalt and a little bit of copper and didn't know why. And the inorganic chemists came in and started bringing those two communities together, and the field has taken off since then. So I wouldn't really worry about what background you have. I would try to figure out where you're excited to spend your career, or at least start your career.
Going past bioinorganic chemistry, would any of the panelists like to comment on the idea of having the right background for multidisciplinary research?
I can, Kate was saying something.
I can go first, but you can, I'm sure you'll have a good perspective also on this. I would say I was actually really intimidated to join the Elman lab, which is the lab I eventually joined, because I wanted to do reaction development and had no experience with metals. I had never even taken organometallic chemistry, so I was very intimidated. The lab was centered at that time, and still somewhat largely around rhodium catalysts. But I would say I did it, and it was really no problem. I took organometallic chemistry in my first year, which was great, but all of your other lab members really are there to help you, and the postdocs in the lab are super helpful. Your actual PI mentor is very helpful. So everyone's there to help you learn, and I wouldn't be too scared to try sort of bioinorganic chemistry if you have more of a bio background at all. I think that's really exciting.
Yeah, and just to follow up, I agree with everything Kate said, and I had a similar experience. I came into Zion's lab trained in some organic synthetic chemistry and had never, built a spectrometer, worked with a spectrometer other than kind of the ones where you just put samples in. But if you're getting into spectroscopy, this is a home-built, really complex instrument. So I had no experience on that front. But I think aside from all of the resources that Kate just mentioned, which are great, also I think Yale, the graduate department in general is very fantastic, because you have your required classes that you have to take in really in your first year. And then you're kind of done after that and into research. But most professors will let you audit the courses. So if you wanted to just either go into some completely different field or learn about something that you're not, familiar with, just auditing that course is very easy in the Yale chemistry department. And I know I audited probably 3 or 4 courses just to learn more and kind of freshen up on different things. And so that's just another resource that was available outside of all the stuff.
Yeah, I have a complementary addition. So my group is very interdisciplinary. And as you follow the data, which is what we're trained to do, sometimes that data takes you into zones where you're a little uncomfortable. And that's a good thing, right? So you follow the data. And what's nice about Yale is the boundaries between individual labs, as we just heard about, or even departments and institutes, or even campuses. Those boundaries are very small, and people are here to help you. And in fact, they'll be excited that your data has taken you into uncharted territories. So there's a lot of support here that is very wide and very good. So, and that's one nice thing about Yale. Again, we're very social, and the boundaries are very low. So, thanks.
Okay. Moving on to another question. This one is about barriers between universities and industry. I don't know if anyone would like to comment on that aspect, in addition to the barriers between labs being low. What about research between academia and industry?
I guess I'll take that one, since So a lot of the students, they go straight into industry, and a lot of the faculty here have contacts that can help you get industry positions. Additionally, especially in the organic division, a lot of us work with industry and have grants through industry where, you know, we kind of partner, in fact, with certain industries to make advancements. And then the third area is sometimes individual labs will create startup companies themselves. And, you know, the best people to actually lead those startup companies are the students that actually did the work. So we have examples where students literally took their PhD project and then started companies. So I don't really know Jacob's background, but maybe he could comment a little on that. Was your project related to anything you did in your PhD or no?
It was actually completely unrelated. That said, we have 3 alumni, well, me, myself, and then 2 other alumni. So one from the Herzon lab and one from the Miller lab are actually both employed at Treehouse. And so we met at Yale during the actual happy hours that are monthly hosted there. And we would talk and we would chat, and they were both interested in going down that pathway. And so they're still employed there today. And another one of our employees came from Vanderbilt University where, but I met him at undergrad. And so in that sense, very similar story, you know, but yeah, so we have 3 Yale alumni there, though it was not generated from a project at Yale.
We have a question, and I want to make sure to be able to hear from all of our panelists. So if you'd like to thumbs up a question, then please go ahead, panelists. So a question is, with the research scene ever changing, how do you determine what you want to work on while adapting and keeping up to the frontiers, especially for a PhD program, which is only 5 years?
I guess I'll say that what you learn as a PhD is how much you don't know. That the amount of science that's out there is so enormous, you have to spend your whole life learning and reacting to changes. And it's one of the exciting aspects of getting a PhD is you learn how to do that, and you continue your passions for your whole life in keeping up with things and following your interests. And so you shouldn't view it that you're going to learn what you learn in the PhD and then you're done. It's really just learning how to learn, and then you learn the whole rest of your career.
Okay, here's another question. How did you know what research you wanted to pursue when you applied? Is it possible to change research tracks or labs once already in your PhD program?
I feel like I'm talking too much here, but so if anybody else has stuff to say, but again, I think uniquely, I came in as like, I want to do organic synthesis and I want to work for like, you know, these couple labs. And that was my goal. That said, and again, another great thing about the chemistry program at Yale is when you come in, you don't join a lab until your 2nd semester. So the whole first semester, you kind of do rotations in labs. And it's either 3 or 4 usually with the labs you choose. But at the same time, you can do double rotations if you're interested in, you know, more than those 3 or 4 labs. And so that's what I did. I think I did like 5 rotations, and those rotations are really just kind of meeting the lab, meeting the professors, getting to know the research. It's not a lot of work. And also the first like kind of, I think, month you're there, all of the professors present their research and you get to kind of meet them and know them. And so I thought it was very easy. I came in organic chemistry. I think I stayed on the quote organic chemistry track the entire time, but I ended up doing a lot of materials chemistry, spectroscopy, physical chemistry, and really didn't do that much organic chemistry. So it was very easy.
So that was very similar to my experience, even though my experience was many years ago. I didn't know who I wanted to work for when I came to Yale. When I was interviewing at graduate schools, what struck me about the Yale chemistry department is that there were probably at least 6 different labs where I felt like I really liked what they were doing and felt like I could do that. And so I had the opportunity to do rotations through 3 of those labs in my first 3-4 months. Actually, the first year I had a biophysics training grant. And so it was a really great opportunity to, work with the professors, work with the other grad students and postdocs, and really, identify where my interests were and what area of research I wanted to focus on. So that was a really great aspect of the Yale chemistry program.
Fantastic. We have a question about research in foreign countries. The question reads, I would be interested to know whether any of the panelists have experience conducting research in a foreign country. Did you encounter any difficulties, i.e. with chemical nomenclature?
Ziad, you should take this one.
Yeah, I mean, I can answer this question. So I was a postdoc in Germany after I finished my PhD. I had lived on the West Coast, I had lived on the East Coast, and I wanted to see whether what science was like in other countries and different funding systems, different cultures. So I was a postdoc at the Technical University of Munich. And even my, my training in high school German and taking German classes when I was there wasn't enough to really read through some of the papers right away. So the thing that I was very pleased about is that the lab was very international. There were people there from Italy, from Ukraine, from France, from Spain. And so we spoke English. And it was perhaps a situation where if they were all one language speakers together, then they might revert to a different language. But speaking English puts one in a very good situation for conducting science in other countries. I didn't have serious problems with that, but I guess your mileage may vary. Okay, so let's move on. Can I apply for spring 2021 intake at Yale? We actually do not have an incoming class for spring 2021. The typical cycle is that you'll apply in the fall, and then acceptances will come out and decisions will be made in the spring, and then you will begin graduate school in the next fall. I have a question here. I am studying chemical engineering, but I am interested in going to graduate school for chemistry. Are there any difficulties or considerations I should be aware of for someone with an engineering background coming into chemistry?
I don't know. Maybe you could answer this too, Ziad, but I know when I was leaving, we had a chemical engineer, Chishan, come into the lab and work with Ziad and I. And I would say that there doesn't seem to be any issues at all. He's a fantastic, I think, member of the lab and has been fine at doing all of the chemistry research. And I think, engineering, maybe the undergraduate education is a bit different than science, degree, but I think the skills are very similar. And then the grad school experience, as so many people have mentioned, is really kind of, once you're there, it's all about learning to learn. And so wherever you're starting from, whether it's biology, chemistry, physics, engineering, or even, potentially different subjects, once you're there, it's all about learning and growing from that point, moving on. So.
I would agree with that. In my experience, and I don't know how the chemical engineering major is at your school, but the typically chemical engineers will take a lot of the same classes that chemists take, and then more classes on top of that go into engineering. So I think a chemical engineer would have a pretty good background for chemistry graduate school. And if one important skill that we've heard time and time again is the ability to teach yourself. And so if you come in with this right mindset, I think with an engineering background, you should be totally fine. So here's a question. Between research experience and GPA, which one is valued the most?
I guess I can answer that one. I mean, I think research experience is clearly very important. But on the other hand, during these COVID times, I think we all realize it might be hard for some people to get into the labs. Some universities aren't letting undergraduates be in the lab. So in normal times, I think research experience is probably more important. And also GPA has many different meanings. You know, GPA, depending on which classes you took and which, you know, of course, the science and math classes are going to be more important than the other classes. And if we see improvement over the years, that can also be, you know, an important metric. So I think we really don't look at only one factor in admissions. It's really a linear combination of many different factors, and the weighting really depends on a student. It depends on the field. So I think there's not like a formula. It's not like an algorithm where we plug it in and decide. We're really looking at the whole application and the person as a whole, and taking into account all the different aspects of you know, their personal statements also important, all these other aspects. So I think you don't want to focus on only one thing. I think, you know, you put your best foot forward, and certainly try to get research experience if you can.
Anybody else like to comment on research experience and GPA? From an applicant's perspective, the research experience is really something that will let you know if this is going to be something that you'll enjoy doing. So I would say trying to see what your life is going to be like as a graduate student by getting some research experience, even if it's remote or somewhat in a different form because of the COVID situation. I think that's really a good way to mentally prepare yourself and to think about all of the challenges that you might be facing, and just to see if you enjoy the lifestyle. Okay. So we've had lots of great questions. Unfortunately, we won't be able to get to all of them. So I would like to thank all of our panelists for fantastic presentations, for fielding questions brilliantly. And I want to encourage all of our attendees to tune in next week, where we'll be finding session 2. And during session 2, I guess what we'll be doing is we'll be presenting you with red, green, and blue photons that are guaranteed to reduce uncertainty that you might have about getting that first research experience. So thank you a lot. Thank you so much, and we'll see you next week.